Okay, so for problem number 3, they give us an image of a 3D image of the wire here, but imagine you are looking at the wire from the side. I was trying to draw a camera and then I turned it into an eye, but if you're looking at it from the side or taking an image of it from the side, you would see the end of the wire and the current would be going into the page. So I like this image a lot better. We can see what's happening and interpret it a little bit easier using diagram and B. So for the first step, we are going to start with the direction of the magnetic field. It tells us that the wire is pushed to the right, and so we know that there is going to be some sort of magnetic force pushing it to the right. We are going to use the right-hand rule, knowing the current goes into the page and the magnetic force is pushing right, then that means there has to be a magnetic field going upward to cause that magnetic force to go to the right. So for the first one, the direction of the magnetic field is up. The second part of this question is asking to show all forces applied on the wire when it is in the field. So I already added one force. Let me add the second force, which is my mass times gravity, and then my tension, which is pointing upward. Okay, so for C, it says find the magnetic field using the following information. We've got a component of the tension force pointing upward, and since the angle is here, alternate interior angles translates it there. So the vertical component is cosine, and then the horizontal component going this way is sine. That lets us know that we've got the magnetic force equal to the tension force sine of theta, and we've got the gravitational force equal to the vertical force, which is cosine of theta. Now I'm going to plug in this Ft into that. So Ft for this equation is force of gravity over cosine. And you can see that when I plug it into my Fb equation, I get force of gravity over cosine times sine, which is just force of gravity tangent theta. From there, it asks us to find the magnetic field, and we get the magnetic field from the magnetic force equation. Since it's a current, I use the ILB equation. Force of gravity is mg, and tan theta is my function, my trig function. I'm solving for magnetic field, so I get mg tan theta over current times length. And all of this information is given to me, so it's a simple plug it into your calculator. Mass is 0.05. Gravity, I'm going to use the value of 10. Tan theta is 18 degrees. And current is 2.5 amps times the length of 0.4. And when you plug that into your calculator, you end up with a value of 0.16 Tesla. Okay, so for part D, we've got two current carrying wires. I wrote down all the values here. Mass is 0.05, length is, the length of the wire is 2, degrees is 1.5, and the length of the string is 0.9. And what we want to find is the current in each wire. So what's going to happen is each wire is going to create a magnetic field on the other wire, and that magnetic field is going to cause a force. And if you analyze it, which I'm not going to do, you're going to see that those forces are going to repel each other. So the first thing we want to do is we're going to stick to our equation here of magnetic force is equal to mg tan theta. So I've got ILB is equal to mg tan theta. We want to solve for current, but the problem is we don't have magnetic field. The magnetic field equation we solved for here, because we used this equation to solve for magnetic field, we can't plug that in. So we need to use a different equation for magnetic field. And one of the equations I told you to memorize is the magnetic field of a wire. So that would be mu naught I over 4 pi r. So let's plug in our equation for the magnetic field of a current carrying wire into our magnetic force equation. So I've got IL mu naught I over 4 pi. R is the distance between the charge and the location where it's creating the magnetic field, which is all the way to the opposite charge. Now, because we don't have that distance value, but we do have A and we have an angle, we can use our SOHCAHTOA to figure out what this length is. So it's opposite over hypotenuse, so 0, well, let's just call it A sine of theta, but because we need the full distance, the radius is really 2A sine theta. This whole thing is equal to mg tan theta, and then I want to solve for I, so I'm going to isolate the I squared, and then divide the other variables to the other side. So I'm going to multiply by the reciprocal. I've got the 4 and the 2, that becomes 8 pi. I've got A and mg, and I've got 2 trig functions, sine theta, tan theta. In the denominator, I'm going to divide my length and my mu naught, and then I'm going to take the square root. So what I want to point out is, as you're plugging in your values, you can simplify things. I'm going to go ahead and plug in values and not simplify it to save time. I get I squared is equal to 8 pi. A is 0.9, mass is 0.05. Gravity, I'm going to use the value of 10. Sine of 15 degrees times tangent, 1.5, and tangent of 1.5. The length of the wire is 2, and mu naught, this is in your equation sheet, is 4 pi times 10 to the negative 7. So you can see that the pi's are going to end up canceling out. The 4 and the 2 are going to cancel out with the 8 here. So quite a few things simplify. In the end, I mean, you could just plug it in as is. I end up with an I squared is equal to 1,542, but I still have to take the square root of that, and so when I take the square root, I get a current of 39.2 amps.